All right, everyone, we are back and we are going to go through our problem set 8 solution video. So we're looking at the basically a torsional pendulum. Should look familiar from our friend, the spring mass damper system. Yeah, So we're given essentially some of these parameters here. Dirac delta unit impulse. So basically, we know that our input to our system is going to be equal to basically just unity. So we'll just have this. We can use our transfer functions as usual. I need to have an overshoot less than 18%, a peak time less than 2.6 seconds, and then a settling time less than 4.6 seconds, 4.7 seconds. So we need to see, does the system meet the constraints, prove and verify it, plot the desired pole region of essentially, these system time constraints, and then redesign the above system to meet the specs. So let's dive right into it. So let's go ahead. We're going to run our functions that we are going to use quite a bit. And first, let's set up and just solve for what we have at the moment. So I always think it's good. I mean, we have some of these parameters, but we can actually solve for these in just a second here. And we'll leave these for a little bit later. So we've got our plant function. This is our settling time goal, and we know how to relate our settling time goal to sigma. So we basically have a sigma right here. So let's wait for Mathematica to wake up for just a second. Let's go ahead. So this is our sigma. So we need to make sure our sigma pole is going to be greater than this value. We can also relate our peak time to omega. So we can use that to figure out, okay, we have our omega value. And then we're also saying that we need the overshoot to be less than 18%. We can use that to solve or actually put bounds on our zeta value. So we've got sigma, we got omega, we got zeta. Now we just kind of need to have like a limit of what our omega n has to be, or at least greater than. So we can actually plug in and figure out what is, and we can solve for, we have omega. We said, right, that needs to be equal to or greater than this. We have our zeta, which we pulled from right here. So now we can solve for omega n, and we've got our value here. So this is essentially where we want to work with and how we, what we have to kind of look at. So this is our transfer function. We can look at our transfer function poles. We can see some of these values, and we can fill in our pole allowable regions with our zeta, with our omega n here, and with our sigma here. So, or actually, excuse me, not our sigma, our omega. So we can go ahead, plot this function. Oops, it's going to give us an error. Let's plot this, and let's plot this again. I'm going to actually kind of bring us over here for a second. So looking at this, and it's always nice to kind of verify. Let's look at, and let's see if we can get some coordinates here. We can see this line. So everything has to be to the left of that 1.2 something. So that's giving us we can look at it over here. That's giving us that omega value, right? And essentially, yeah, our omega value in here. So we can actually move. Actually, we can see the TP value because we're going up here. So remember, we have to set our sigma minimum and then our eta first. So we have that eta. We also have our sigma min. Actually, excuse me for just a second. I think we need to rearrange this to be, I think this needs to be 0.9. This needs to be our sigma value here. As such. So let's go ahead, paste that in right here. Paste it in. It's not going to change much, but at least now I think this is much more correct. So again, everything has to be to the left of here. It has to be within essentially that radius, which is defined partially by the eta, and then we also have that angle of our omega n as well. or vice versa. Yeah, that zeta is eventually going to give us essentially that angle, and we're going to use that to relate to it. And we also know that omega n is really important for, again, that it has to kind of lie on that line, that magnitude here. So, all right, it looks like omega n defines this kind of circle here. It lives in this circle. This angle, that's that zeta. So, for example, if we change this, so it's actually quite fun to play around with it. So if we make this 0.1, you can kind of see the parameters. So we're changing essentially the angle here. Similarly, if we change this to, if we change this to 0.5, you can see that really change. So if it's 5, now we're really getting in there. So you can kind of see how those parameters change. So just be very cautious. And it's fun to see and make sure that I don't make mistakes either. So we got this here. Excellent. We can look at and see, did we, with our system, are we hitting those metrics that we kind of just defined? So we can actually solve for, here's our standard 2. Here would be our omega n values, our zeta values, and essentially we can see where do we fail. So we said that our sigma has to be greater than 0.97. So our sigma, we failed automatically. What else? We said that for our omega has to be greater than 1.2. Where's our omega? Omega, we're okay. So that's nice, right? But what about our zeta? Our zeta had to be greater than 0.44, and we failed that one too. So we need to start to look at, okay, well, what can we actually change and solve for in order to hit our metric? So how can we figure this out? What's the parameter that we can change to significantly change essentially that system? Well, we have this relationship here where we have s squared and then 2 zeta omega n. So our omega n, we said, we're completely fine. So let's just keep that as it is, right? And we need to figure out this zeta. So we said zeta has to just be greater than 0.4. So let's just plug it in for 0.6. And we know that this functionally has to be equal to, this normalized value here, right? So if we look at our second parameter, it needs to be equal to whatever this is divided by that big I, right? Like, so when we normalize it, it just needs to be this divided by that. So we can solve for what does the value of this parameter have to be? So what has to be effectively my b theta, right? Effectively my damping coefficient. So we solve for that, and we can see if we set that b theta to this particular value, so let's just do our test function here. And now we have our transform function model. We've got this, and then we've got all this good stuff here. And I want to make sure that we're using the same parameters here. So let's go over here. And now I want to put this in right here. Look, we put our function now right here where we hit all those specs. Fantastic. Now, you could go ahead and you can verify, and you can actually see we do it here. We can verify now our new value. So our zeta is 0.6, our sigma is greater than here. We're hitting all those metrics, and we can see that we're good to go now. Awesome. Fantastic. So there's you can also look at the time response. That would be a nice little extra credit if you can do the time response and verify those values as well. Should have made you do that, but I'm being very nice. Excellent. So let's look at this system, and we're going to calculate that settling time, maximum overshoot, rise time, peak time from this command input. So again, we can look at it. Now, you can do this multiple ways. So we can just say, for example, we can get these values, and we can solve for everything right here. And you can see this is our settling time. This is our overshoot, which would be 35%. This is our rise time. This is our time to peak. Or we can look at this and we can verify this function mathematically. So I'll be looking forward to, again, you should run through this and make sure, but you can actually see that peak time is verified right now. You can kind of look at the maximum overshoot versus 1, so 1.35, roughly, right? So I want to see you verify all this. I'm not necessarily going to do that in this video, so but I want to see yours. All right. Determine whether transfer functions below are stable, unstable, or marginally stable, and we're going to verify all our answers here. So let's go. Well, right now, the second order system, these are all positive. We know that's stable. That's our rules. Ooh, third order. Ooh, third order. Oh, fifth order. Oh, third order. We're going to have to use Ruth table for all of this, right? So let's go ahead and let's go through this. So this is our Ruth table. These are coefficients. HS1, we already know is fine. What about 2? So 1, 6, 11, and 6. These are all positive. There's no sign change. Stable. Sign change here, and that's coefficients for the next one. So basically for system 3, we are unstable. What about here? Unstable. And then finally, here we have some parameters. So if we want to be stable, k has to be greater than 0, and k cannot be greater than 4, right? So there's some bounds here that you'd have to figure out whether it's stable, unstable, or marginally stable even. So make sure you work those out and put those in your problem sets as well. Consider the system below the controller. It uses unity feedback, no noise or disturbance. So if we know that the transfer function is just C of S times P of S divided by 1 plus C of S times P of S. So this is our transfer function here. Determine the values of K required for stability. It looks to be, and it indeed is, if we take this, actually I've already done it here. This is a third order function. So we need to use our Ruth Hurwitz analysis. So now essentially we have some bounds here. So K has to be greater than 0. And as we can see here, it has to be less than 4.16 to be stable. We can verify that here. So I'm just a little bit negative. So for example, if I'm 1, you can see I'm right off that axis. I'm stable. But once I get past 4.1, oh, not 4 divided by 1. 4.1 actually makes sense. I'm right on that 0. And if I start to get to, let's say, 6, now I push myself and I'm unstable. Excellent. Control effort. We know the control effort function, which is just C of S over 1 plus C of S times P of S. Assuming now there's some noise and disturbance, derive and show the steps to determine regulation of the system, as well as that expression. So this is actually regulation. So we have those in our notes. Make sure you kind of show us all the steps, but that would be our regulation transfer function. So that's pretty much it for this problem set. Again, make sure you take the steps to make sure that you're clear and kind of visualize some of these things as well to make sure you're confident, but we'll see you in the next and the last problem set. Good luck on your upcoming exam. We'll see you next time. Thanks.